An industrial refinery is a labyrinth of pressure boundaries. Millions of gallons of volatile, high-temperature fluids are continuously forced through an endless network of steel. To build and maintain this maze, engineers rely on isometric drawings. If you look at one of these blueprints, you will see two numerical designations printed side by side, a pipe schedule and a flange pressure class. It is common for junior engineers and field inspectors to read these numbers and assume they speak the same mathematical language, that both are direct statements of how much pressure the component can hold. Trusting those numbers at face value without understanding their distinct engineering origins is a direct path to catastrophic system failure. A schedule number and a class number are built on two incompatible logics. When you translate the ink on a drawing into massive steel components bolted together in the field, these distinct ratings are forced to mate. Treating a flange class and a pack schedule as identical metrics is the quickest way to underdesign a high-pressure system. A flange class and a pipe schedule answer two structurally different engineering questions. The first language is the class rating, defined by the standard ASME B16.5. This designation applies strictly to forged and cast components, like flanges, flanged valves, and fittings. When you see a class rating, you are looking at a direct pressure limit that is pulled straight from a published code table. The second language is the schedule rating, defined by ASME B36.10M. This applies exclusively to straight, welded, or seamless pipe. A schedule number carries no published pressure data. It is a dimensional standard for wall thickness. To know if that pipe is safe for your process, you must calculate its pressure capacity yourself. The central challenge of piping engineering is making these two distinct code languages speak to each other so they can safely contain one continuous fluid pressure. Many assume a class 150 flange holds exactly 150 psi. In reality, the relationship between that number and actual pressure is far more complex. At room temperature, a standard class 150 carbon steel flange is actually rated for roughly 285 pounds per square inch. This chart shows the allowable pressure of a class 150 flange relative to design temperature. The class number serves as a non-dimensional coordinate. To find the pressure limit, you must cross-reference it against the specific material and design temperature. Watch what happens to the class 150 curve as the environment heats up. The pressure capacity drops rapidly. That flange only approaches a 150 psi rating when the temperature reaches nearly 540 degrees Celsius. By mapping class 300 and class 600 on this same chart, you can see how higher numerical designations scale the overall pressure capacity upward across all temperatures. The physics dictating this curve are straightforward. As heat rises, the yield strength of the metal falls. The flange physically weakens, forcing the allowable pressure to be derated. ASME has already executed the complex stress equations for every material group, generating these direct lookup tables. A class rating is a dynamic, pre-calculated curve that bends to the forces of thermodynamics. Straight pipe follows its own logic. There is a common assumption that Schedule 80 is a synonym for high-pressure service, but the designation carries no direct pressure data. As established, a schedule number gives you zero published pressure data. It strictly dictates physical geometry. This cross-section shows the law of fixed outside diameters. A standard 6-inch pipe must have the exact same 168.3 millimeter outer diameter, no matter what its schedule is. This allows engineers to standardize structural supports and fittings across an entire plant.
When a pipe jumps from a standard Schedule 40 to a thicker Schedule 80, the fixed outer boundary forces a structural compromise. The extra metal grows exclusively inward, shrinking the inside diameter. To gain that heavier wall thickness, thicker schedules restrict the flow of fluid through the pipe. But wall thickness alone doesn't grant you a pressure rating. You are missing a critical variable, the material's allowable stress. A heavy Schedule 80 pipe forged from a low-strength metal, operating at high temperatures, can rupture before a thin Schedule 40 pipe, made from a high-strength alloy. A pipe's schedule tells you its geometry. Until you run the yield strength of the specific material through a formula, its pressure capacity is unknown. To keep these engineering logics clear in practice, you can rely on a simple operational rule. Class is a read-forward system. You start with the flange designation, look at the table, and it hands you the limit.
Schedule is a read-backward system. Start with required design pressure and work backward to figure out the dimensional designation you need. This is the ASME B31.3 code design equation. It is the mandatory tool for that backward calculation. You plug in your design pressure, P, and the material's allowable stress, S. The equation computes the minimum required wall thickness. You take that raw output and round it up to match the nearest standard schedule block in the B36.10M catalog. The published codes have done the mathematical heavy lifting for flanged joints, but they demand the engineer prove the physics for the straight pipe. This theoretical workflow translates directly into applied design during the engineering phase of a major industrial project. Imagine a pipeline designed to handle an internal fluid pressure of 10 megapascals at a blazing 300 degrees Celsius. This environment requires a parallel workflow to properly size system components. On the pipe track, the 10 megapascal requirement feeds into the B31.3 formula. After calculating required wall thickness, the math forces the engineer to round up to Schedule 80 pipe. Meanwhile, on the flange sizing track, the 300-degree temperature derates the steel. The engineer looks at the B16.5 table and sees a Class 600 flange will fail under these thermal conditions, forcing them to select a Class 900 flange instead. The resulting isometric drawing will call for a Schedule 80 pipe bolted directly to a Class 900 flange. To the untrained eye, those two numbers seem unrelated, but they represent the exact mathematical pairing required to safely enclose the same fluid conditions. Field inspectors and builders are not expected to perform these dual mathematical calculations from scratch on the job site. Industrial projects rely on a piping material specification, or PMS. This is the master blueprint that bundles the correct class and schedule requirements together for a given line. When an isometric drawing lists a pipe class, it points to this specific pre-calculated PMS bundle, providing a single reference for the entire assembly's material requirements. This specification dictates exactly how millions of dollars of steel will be physically assembled and laid into the earth. This creates a dual responsibility for QA/QC teams. They must verify the actual wall thickness on the material test certificate against the required pipe schedule, and they must independently verify the physical stamp on the flange to ensure it meets the pressure class. Never mistake a dimensional standard for a pressure guarantee. Always trace the numbers on the blueprint back to their governing logic, because assuming a pipe schedule and a flange class are the same thing is an illusion the code will not forgive.